Hi everyone, today I'm going to be talking about some ongoing work that I've been doing with my collaborator Cailey Condit on the time evolution of subduction zone thermal structure. We know subduction zones are important as sites of earthquake and volcanic activity and as where volatiles are cycled into the mantle. All such processes are highly temperature dependent through, for example, the high temperature dependence of metamorphic phase transitions within the slab. From a geodynamics perspective, much of the modelling focus has naturally been on understanding the thermal structure of Earth's present-day subduction zones, but a highly related question is how and how rapidly thermal structure evolves through geologic time. An understanding of this is needed to interpret geological subduction zone observables and also to constrain how rapidly volatile cycling may also evolve at subduction zones. And so we target two main questions. So firstly, how does subduction zone thermal structure vary through geologic time? And second, what are the potential geologic consequences of this variability? So the first models of subduction zone thermal structure were in the form of analytical solutions. And these analytical solutions were extremely instructive in demonstrating that this type of flow in the mantle wedge, which is sometimes called corner flow, is what exerts the fundamental control on mantle wedge and slab top temperatures. Over the past few decades, numerical modeling studies have become more prevalent and allowed us to incorporate additional rheological and geometric complexities into these models so that they can then be applied to real Earth subduction zones. Both modeling strategies have shown the first order control that subduction properties like convergence rate, slab age, and to a lesser extent dip have on subduction zone temperatures. In the context of this talk, it's however important to note that numerical models of subduction zone thermal structure are often steady state, with these steady state solutions being derived by holding subduction zone properties constant over a prolonged period of time. And so to get at time dependence, as is the goal here, we need a complementary modeling approach that's time dependent and also dynamically consistent. Significant time dependence in subduction properties like convergence rate is expected from tectonics and plate kinematics related observations, and also from dynamically evolving large-scale subduction models. So given this time dependence in subduction properties and the links between these subduction properties and subduction zone temperatures, a significant time dependence in the subduction zone thermal fields seems likely. And this is attested to by a range of geological observables, both at individual subduction zones and at a global scale. Here is the global compilation of pressure temperature conditions recorded by exhumed rocks at oceanic subduction zones by Agar et al. And I just want to draw your attention to the right figure, which shows the temperature recorded in these rocks relative to relative subduction time. And so from this figure, it's clear that subduction zones are hottest in their infancy, as recorded by the metamorphic soils shown in red. And then subsequently, there's a lot of scatter, but perhaps a cooling trend. And so it's this type of observation, both at an individual subduction zone scale and at a global scale, that we're interested in developing a dynamically consistent basis to understand. To do this, we use the Aspect Finite Element Code, which is open source, to develop 2D time-dependent subduction models. And so you can see the time evolution of the viscosity field and the thermal field in one such model. And in addition to being time-dependent, crucial components of these models are that there are no forces or velocities imposed on the subduction zone, so they're dynamically consistent. And we solve for flow within a domain that spans the entire mantle. And so both of these factors combine to basically enable the subduction zone to evolve naturally and dynamically consistently so that we can then investigate the effect of the various dynamic phases on subduction zone temperatures. I also want to note that all this work is currently in review at G-Cubed, and to highlight some previous studies that have looked at time-dependent subduction zone thermal structure. And in particular, this Kincaid and Sachs study that, despite now being over 2 decades old, is a great modeling study which inspired and instructed some of the work that I'm presenting here. In addition to being time-dependent and dynamically consistent, another important feature is that we use a weak crust to decouple the two plates. We focus our thermal analysis on this crustal region, both its upper surface, which is the slab top, and its lower surface, which is the Moho, and we remove the weakening associated with this crust at a constant 80 kilometers depth, which is broadly analogous to a maximum depth of decoupling as is imposed in some previous studies. Another important aspect of this model, which is a really nice feature of the aspect code, is adaptive mesh refinement. And this allows us to have really high resolution in our crustal region where we're doing our analysis, but much lower resolution in other regions of the model where there's less going on dynamically. To summarize the main dynamic phases of our model, so subduction starts with an initiation phase where the slab forms from an initially flat-lying plate. We then have the free sinking phase as the slab rapidly sinks through the weak upper mantle, and this is associated with very rapid convergence rates. And lastly, we have a mature phase, which corresponds to the time after which the slab has touched down on the lower mantle, and this is associated with very low convergence rates. So here I show the convergence rate evolution through time in black and the slab dip evolution in brown. And so in terms of the convergence rate, again, you see this very rapid convergence during this intermediate free sinking phase and much slower convergence either side of this intermediate phase. And then the slab dip is less variable, but it exhibits a gradual decrease as the model evolves. So the take home here is that when you allow the slab to evolve dynamically consistently, temporal variations that are significant emerge in these parameters. Now I'm plotting some temperature indicators, so for the slab top in yellow and for the Moho in red. And so the middle panel shows the depth of a constant isotherm within these two regions. It's the 500 degrees isotherm. And then the bottom panel shows the temperature at a constant 100 kilometers depth. And so what you can see is that there's a similar degree of time dependence in the temperatures. Okay, so we have very rapid cooling of both the slab top and the Moho during initiation, and then subsequently the slab top cools at a reduced rate. The Moho has a more complex evolution because it has a rapid cooling transient during this intermediate free sinking phase, which is basically due to these rapid convergence rates. I now overlay the thermal thickness of the overriding plate in black and the decoupling depth in gray. And so you can see that there's a first order match between the depth of this slab top isotherm and the decoupling depth. And the decoupling depth is something that emerges from our models naturally, and it's also plotted within these thermal zoom-ins. And what happens is the decoupling depth, which is basically the vertical extent of the cold and stiff mantle wedge corner, it increases as the model evolves and the upper plate thickens thermally. And what this does, this thickening, it produces more and more cold material above the slab, which in turn is responsible for this gradual cooling trend of the slab top as the model evolves. So we've checked that these systematics hold for a wide range of additional model parameters. And to summarize the relationship between the subduction temperatures and the subduction parameters, we find that the slab top is dependent mainly on this decoupling depth, or more generally the thermal structure overlying the slab, and that the Moho temperature depends primarily on the convergence rate. And so these two links are not new. They've been demonstrated in previous steady state modeling studies. But what is more interesting is that when you couple these links with a dynamically evolving slab, we get these thermal phases which emerge self-consistently. So again, we have rapid cooling during the initiation phase. During the free sinking phase, the slab top cools less rapidly, whereas the Moho has this quite extreme cooling transient. And then during the mature phase, temperatures become more constant. I now show the slab top thermal evolution in a slightly different way. So here are the pressure temperature paths along the slab top and how they evolve with time. We have this gradual cooling trend going in this direction as time evolves with significant time dependence. And then recalling the link between the decoupling depth and the slab top temperatures, I also overlay the decoupling depth on these three highlighted phases. And so what you can see is that all slab top paths have a kink in them, about 10 to 20 kilometers deeper than the decoupling depth. And this kink becomes more pronounced as the decoupling depth increases as time evolves. And it becomes extremely pronounced as the decoupling depth basically approaches this depth at which we strengthen the crust, or this 80 kilometers maximum depth of decoupling. This strengthening depth basically acts to limit the decoupling depth from going any deeper. Now also plotting the Moho PT path evolution. Again, they demonstrate significant time dependence. All of these paths are colder than the slab top paths. And perhaps what's most interesting is that in contrast to the slab top, these paths are not cooling throughout the whole model evolution. Rather, we have cooling from the initiation phase to the free sinking phase, but then we rebound back to warmer conditions during the mature phase. And this is just another way of representing this cooling transient that occurs during the free sinking phase is associated with rapid convergence rates. I now overlay the exhumed rock compilation on the slab top PT paths. And it's interesting to note that the slab top PT paths sweep through much of the pressure temperature space represented by this global compilation of exhumed rocks. And so this suggests that in addition to the wide range of subduction parameters that Earth's subduction zones have, perhaps a significant component of this exhumed rock PT space is due to the dynamic phases that subduction zones evolve through as they age. One of the main simplifications in our approach is how we deal with the crust in a relatively simple way. We give it a constant viscosity and we strengthen it at a constant depth. And so in order to get a handle on the effects of this simplification on our thermal state, with particular focus on the slab top PT paths, as shown again here for the reference, we examine two additional cases. So firstly, a case as shown in the middle where we allow the crustal weakening to go much deeper, and then another case where we give the crust a viscoplastic rheology with a very low yield stress as previously implemented in the studies listed at the top. We find that in these two additional tests, the decoupling depth continues to increase throughout the entirety of the model evolution, which ultimately, towards the end of the model, results in mantle, wedge, and slab top temperatures, which are too cold relative to first order petrological constraints. And so this seems to suggest that as implemented in our models, that some limit to the decoupling depth that's reasonably abrupt at approximately 80 kilometers, maybe plus or minus 20 kilometers, is required by these dynamic models to limit the temperatures to reasonably warm conditions. And this is interesting because this has been suggested in a whole host of previous steady state models, including those listed above, and this is why we chose this 80 kilometers depth. But this also seems to be supported also by our dynamic modeling approach. Another note is that the thermal state is relatively independent of how we actually parameterize the crust in the early stages. It's only as this decoupling depth approaches its maximum that this becomes an important effect. I'm lastly going to explore some of the implications that this time-dependent temperature evolution has for the metamorphic phase transitions that occur within the slab and hence slab dehydration. So to do this, we couple our PT paths with perplex models for the thermodynamic evolution of mineral water-saturated slab top material, which we assume is mid-ocean ridge basalt, and Moho material, which we assume is depleted mob mantle. There's lots of simplifications in this approach, including these bulk lithologies, but we do this just to get a first-order sense of slab dehydration. So when we do this, we find that during initiation, the slab top has dehydrated completely by about 50 to 60 kilometers depth. In terms of the Moho dehydrates at deeper, approximately subarc depths. During the latter colder phases, where the slab is much colder, we find that the slab top dehydrates at about subarc depths, whereas the Moho transports water all the way past the subarc. So this just suggests that significant time dependence in crustal and mantle dehydration can be expected to be associated with these time-dependent thermal phases. So to quickly wrap up, we find that in our models, the thermal state of subduction zones is highly time-dependent. It's dependent both on the dynamic subduction phase, so for instance, the relevant convergence rate, and also on thermal structure inherited from previous phases via, for example, the increase in decoupling depth. We identify three main dynamic thermal phases corresponding to initiation, free sinking, and mature subduction. And I'll just note that this free sinking phase is characterized by a cooling transient at the Moho, which is associated with rapid convergence rates. We expect these time-dependent temperatures to be imprinted on many processes and geological observables, and we briefly explore a few. And we suggest that we need to interpret these particular geological observables in the context of the dynamic subduction phase that is relevant to the timing of these observables. And so that's it. So thank you very much.